nanohub.org.
Online simulation and more for nanotechnology.
All right, let's get started, guys. Now we have started getting into the exciting topics. I was preparing the next lecture, actually, lecture 21. It's gonna be on Markov chain Monte Carlo. And I was preparing it, and it's actually so amazing topics. They're gonna get very, very excited starting next lecture. So today we're gonna work on a reformulation of inverse problems. We're gonna state them as Bayesian inference problems. And we're basically going to get stuck at some point, and this will motivate motivate us to introduce Markov chain Monte Carlo next time. But anyway, let me just get into what I want to talk about today. So first, I'll remind you a little bit about the classical formulation of inverse problems, which is what we did last time. Okay. And then I'll highlight the key problems that you face when you follow the classical formulation. Then I'll talk about, I will reformulate the inverse problems as Bayesian inference problems. So basically, we will state the model calibration problem as a probability problem, right? And it's going to be extremely simple and extremely natural. This is the amazing thing. And this formulation is going to make literally all the problems of the classical approach go away. There is only one issue, and that is you cannot actually follow the Bayesian approach till the end very easily. You need to know a little bit of theory. And part of that theory is Markov chain Monte Carlo and more advanced methods. But seriously, every time you have to calibrate models of a parameter or say something about a quantity that is not directly observed but may affect the outcomes of your model, and that model could either be a model you just made up, like a made up model, a statistical model, or it could be a physical model. It could literally be any model whatsoever. The procedure for calibrating it is exactly the same. There's really just one equation, and the only thing that changes is what goes inside that equation, and the way you then solve for that equation. So I'll remind you that again and again later on. And so the Bayesian formulation is analytically intractable. That's the only problem, if that is even a problem. Well, it is what it is. It is the right thing to do, and it will be an accident if it was analytically intractable. And we're going to, because we don't know yet how to sample from complicated things. This is what we're going to learn next time. We'll use the Laplace approximation to come up with a solution. Okay. So the Laplace approximation, we introduced it a couple of lectures ago, and it basically told us how to take an arbitrary probability density and approximate it with a Gaussian. So we're just going to use that. This is not the right thing to do. When you do that, you're actually not fully Bayesian, but it is very easy, and we can just do it. And we're going to demonstrate the Bayesian formulation and the Laplace approximation to the kinetics problem. And then I'll just tell you about some of the problems that remain and why we really need to go into sampling methods. Anyway, so let me just remind you what the problem was. This is the problem we're going to be using. At the end, I was thinking about introducing more problems in the lecture, but I don't see the point. Let's just take this problem and just do the best we can over the course of 4 or 5 lectures. Really no end on how well you can calibrate this problem and how bad you calibrate it if you don't think about it. Anyway, so I remind you that we have a dynamical system that describes basically the evolution of the various concentrations of various chemicals and how one turns into the other. And we have measurements of these concentrations at fixed time intervals every 30 minutes. These measurements are noisy, and we want to go back and infer the reaction coefficients, how NO3 converts to NO2, and so on and so forth. Alright, so the classical formulation is as follows, right? So remember we had a space of parameters of your model, that's what I called X. It's a d-dimensional space, scripted X, and then you have experimental measurements, which you can have as many measurements as you want. To say you have M such measurements, and then you have a model that maps whatever the unknown parameters are to the measurements. Alright, so it connects a model that predicts whatever you measure. And then the inverse problem, I naively stated, is find me an X that makes the model prediction come as close as possible to the experimental measurement. But this, of course, for this formulation is not very, it's extremely ill-posed. First of all, there may not be a solution, it ignores the noise in the data, etc., etc. We generalized a little bit and we said that the classic formulation of inverse problems, what you really need to come up with is a loss function, a function that tells you how much, how bad you feel, if you like, or the cost you incur if your prediction is off, right? So if you predict f of x, and your actual data is y, how bad is that? This is what L of f of x, comma y gives you. And then the idea is to select the parameter that minimize your loss. And of course we said that a very common loss is the square loss, right? This loss. So you say that I want to basically minimize the square error of my model. And then your mathematical problem becomes an optimization problem, right? So the model calibration problem becomes minimize the square loss over x. That's it. And by all means, this is the first thing you should do when you have to calibrate a model. Seriously, right? Why not? But it will not work most of the times. This is how it works for the best solution we found for the catalysis problem, and there remain a few problems. All right. So first of all, and then the issues that you may, let me just mention very fast the issues that you may have. Okay. So the first thing that may occur when you use the classic formulation is that it may not be possible to find a solution. So imagine that we try to create a model that didn't include this intermediate concentration, this intermediate hidden molecule, okay? A model that didn't include that X, which we don't really know what it is. Then there's no way we can conserve mass with this dynamical system. So no matter how well we try to calibrate our model, it's not going to really capture what's going on. It's going to be very wrong, right? There's not really a right model in this case. Basically, the solution may not even exist. And the classic approach does not give you a way to account for that. So it's not going to tell you, look, there is not really a solution. There's something seriously wrong with what you're doing. It's going to tell you, here's the solution. I fitted the data. And then when you try to use it somewhere else, you're going to get garbage. Hopefully you will figure it out at some point that there's something seriously wrong with the model you calibrated, or maybe somebody's going to die. Okay? Anyway, the other thing that may happen in the classic approach, and it doesn't give you a way to figure that out, is that there may be more than one solutions. So, for example, let's assume that we have two hidden intermediate products, X and Y. There's absolutely no problem. You can assume that there are as many as you want, and then you can calibrate that model. And you know what? If it works with 1, it's gonna work with 2. It's gonna work with even with 3. Okay? You're gonna get the goodness of fit. You're gonna get the loss, the minimal square loss that you're gonna get is gonna get better and better and better the more hidden products you add. What is the right number of hidden products? Is it 1? Is it 2? Is it 3? Is it 4? It doesn't give you a way to select your model, right? Does that make sense? So I told you, oh, there must be one hidden product X that I do not observe, and this, fitted the data quite well. But there could be 2 or 3. How do I know that there is 1? Well, I don't know that there is 1. Okay, because I do not even measure it. Is there a way to tell my method, well, okay, there could be 1, 2, 3, or 4, or 5. Pick for me the best possible model. Pick for me the simplest model that matches the data the best. This cannot be even stated in the classical approach. But the Bayesian approach does offer a solution. Okay, but this is something that we're going to discuss in like 4 lectures, model selection. I'm just pointing out that it is not possible to even state it with the classical approach. And the other thing that it doesn't do, the classical approach cannot do, is quantify your epistemic uncertainty. Right? So there's no uncertainty here. It's just, you have point predictions for whatever is going to happen. But of course, it makes sense that you have a finite amount of data, right? And with a finite amount of data, you cannot expect to perfectly, especially when there is noise, you cannot expect to perfectly find the reaction coefficients. Imagine that one thing that you could do, right, is you could measure for more times, and presumably that will reduce your uncertainty about the reaction coefficients, right? So that's one thing you could do. You could sample at intermediate times, and that should also reduce your uncertainty. And of course, you could also observe whatever is hidden, and that would reduce your uncertainty even more. You see what I mean? There's no uncertainty here, by the way, but in reality, there is uncertainty. There's uncertainty because of the noise. There's uncertainty because of the finite amount of data that you're using. And there's, intuitively that the more data you have, the more sure you're going to be about what you find, but this is nowhere to be found here. Make sense? Any questions? So we remember, what is the problem with the classical approach? Well, a solution may not exist and there is no way to figure that out, really. There may be more than one solution and it doesn't give you a way to say which one is better. 2, 3, it ignores epistemic uncertainties induced by the finite amount of data that you have. It is not there.
So
all right.
Whatever solution is not there, will it throw garbage?
Whatever.
The problem doesn't have a solution, will it throw a garbage?
Yes, you will get garbage. So when the problem does not have a solution, when your model is wrong, you're going to get garbage. But you don't know that you get garbage. Okay, that's the problem. So you're always going to fit your data to the best possible extent if you minimize the square loss, for example. But if you take these calibrated parameters and you put them in another situation, there's no guarantee that you're going to get a model that works. So the Bayesian approach solves all these problems. Seriously. Well, of course, there is a catch. Right? The catch is that it's computationally expensive. It takes more effort to formulate things. But that's expected, I guess, from a methodology that solves all the problems. Right? Anyway, so we have the same situation as before. Scripted X is our parameter space, our experimental data, the model. We want to find X that matches the data as well as possible, same thing as before, but now we introduce a little bit more structure on top of these things. All right, so we're going to need to introduce three things. The first thing we need to introduce is a prior over the parameters. So, right, the Bayesian approach requires you to say what you think about the parameters of your model before you start doing anything else. Right, so what are your parameters? Are they positive variables? Are they negative variables? Are they supposed to live within specific bounds? What else do you know about them? Do you have any other, have you done any other experiments that give you some information about these parameters? All these things, you put them inside your prior. Okay? I will say that like at least 5 times today, in case you missed the first time. So the first thing you need is the prior. The second thing you need is a likelihood model. So you no longer say that your model f of x predicts y. Obviously, that's what's supposed to happen. But you need to say how it predicts y. So you need to say, you have to have a model of the measurement process that gives you y. So you need to say, when I am at x, if my model parameters are x and my model is right, what is the probability that I measure y? Okay? So you need to connect your model to the actual measurement. And to connect the model to the actual measurement, you need to model 2 things in addition to your model. The first thing you need to model is the measurement noise, the noise process. You need to say what kind of noise there can be in your problem, right? And the other thing you need to model is the possibility that your model is wrong. So maybe your model has a systematic error. You could this is the place where you put it. Maybe your model is wrong and then you need to add to it a correction. Or maybe the correction is multiplicative. Or maybe the correction is even more complicated. Who knows, okay? But this is the place where this goes, in the likelihood. Now, as soon as you have, and we'll talk about that, so we're going to have one slide on this and another slide on that to talk about these details, this in a little bit more detail. But as soon as you have your prior, and as soon as you have your likelihood, so as soon as you have told us whatever you know about your parameters, and as soon as you have told us what you know about the measurement process and the model error, then the solution of the problem must be this, okay? It's given through the posterior distribution. So you say, what do I think about X if I've seen my data Y? And I'm assuming that my model is correct, okay? This is how this thing is read. What is the best thing I can say about X if I've seen the data Y and my model is correct? Then Bayes' rule tells you that this should be proportional to the likelihood of your data times the prior you have for your parameters. Likelihood times prior. Posterior is likelihood times prior. And this is the normalization constant. So this is just a number that makes this thing integrate to 1 when you integrate over X. And we'll talk about all these things one by one. Alright, so, yes?
What was the F?
F is the model. F is your model. Right? So remember, F is this guy. So everything depends on your model. And the reason I have here F is because I want to allow you in the future to say whether I have an F1 and I have an F2, which one is the best. So even though in most of the books, if you look at, inverse problems, they're going to pretend that F is the right thing. So they're not going to explicitly denote the dependence of everything on F. I'm keeping it in there because in 3 lectures I'm going to come back and say, well, now I have 3 models. Which one is the best? Okay? So, interpretation of the prior. Here's how we interpret the prior. It is my state of knowledge about the parameters of the model before I see any data. How do I come up with that? Well, this is what we did in the first 7 lectures of the class. Okay? Maximum entropy. I mean, probability theory is what we use to talk about our uncertainty about X. What else can you use? You can use maximum entropy if you know the expectation of X or the variance of X. If you can measure some of the X's, then you can use that as well. Do a little bit of Bayesian analysis to come up with that. Or maybe X is also the parameter of another model that you have calibrated already. So you could use the posterior of that calibration as the prior of this one, right? And so on and so forth. And of course, X is, let's assume that X, the parameters are finite, right? So if your parameter was really a function, you have used the Caron-Lev expansion, which we learned in lectures 10 to 12, to discretize it, right? So if your model needed initial conditions, which are functions, or boundary conditions, which are functions, or something like the permeability of the ground, which is also a function, you have already discretized that. Okay? So this is just to show you that the reason why we did everything we did at the beginning of the class is so that we can actually come up with that P of X in the first place. Okay? Alright, so, and seriously guys, if there is one thing that I would like you to know from this class, is actually these 3 slides that I'm gonna write right now. What these things mean. This is what is missing from our community, even from the mathematical community. We don't really think too much about what these things actually mean. Alright, so the likelihood, right? So the likelihood tells us what is the probability that we observe a y if the parameters were x and our model is f. And of course we expect this likelihood to depend on f of x, right? Because f of x is supposed to predict y, so we depend the likelihood to just depend on f of x and not on f on another x, like on x prime, for example. So what is that? It is the probability of measuring y if my model is correct. And we have seen that before, right? So we talked about generalized linear models and how you're just, I mean, there we were basically solving a model calibration, right? But the model was very simple. It was just a linear model in the parameters. And we used Bayes' rule there. Well, it's exactly the same thing now, but your model is not a linear model anymore. It could be a finite element simulation or a finite volume simulation or something more complicated, the black box. Right? But it's the same thing. So lecture 7 and 9, where we talked about generalized linear models, are very relevant here to understand what likelihood really means. And it's really what you think about the measurement error, the process that adds error or disturbs a little bit the actual hidden value that you cannot really observe, and the model discrepancy. So typically people only think that the likelihood is about the measurement error, and they ignore the model discrepancy. And it is absolutely okay to do that if you know that your model is quite good. Okay? But if you are in the early stages of discovering your model and you're not quite sure that you have nailed it, maybe you would like to include model discrepancy. But including model discrepancy is not trivial. I can give you references of how it can be done, but it's really not trivial, of course, right? Because on top of your model, you have to come up with a model of the model error. Okay, so it's a little bit complicated things a little bit, but this is the place where it would go if you needed to do that. All right. Of course, the most common likelihood is the Gaussian likelihood, which basically tells you that the measurement comes from your model, but it is disturbed by Gaussian noise, right? So it's the model f of x plus some Gaussian noise, and it's really that the density of the Gaussian likelihood. Right? So it has this squared error term in there. Again, you will see a connection with the classical approach when you choose to use Gaussian likelihood. But the Gaussian likelihood is not Is it something that you should use automatically? Well, it can be the first thing because, if the noise is small, it will probably look like a Gaussian noise if it is small, right? But in general, it's not the best choice. And for the catalysis problem, actually, it's not the best choice. Okay, because in the catalysis problem in particular, the noise is proportional to the magnitude of the concentration. So if the concentration is very small, the noise is not Gaussian. It is actually skewed towards positive values. You cannot get a negative concentration, for example, right? So we know that for the catalysis problem, the Gaussian noise assumption is not right, especially when for products that have low concentrations. But anyway, it's a starting point, let's say, okay? And I'll show you gradually how you can make a better and better and better model of the measurement process. So let me just tell you what happens most of the times when you're calibrating models. You have spent all this time to create an excellent physical model, maybe even years. And then when you try to calibrate it, you don't even want to spend 5 minutes to think about the measurement process. Seriously, this is what people do. They don't really say, oh, I have 3 things, maybe each one of them has a different level of noise, because I measure these 3 things with 3 different devices, or maybe because they're positive quantities, the noise is going to be skewed and not Gaussian. So that they just say, oh, everything has Gaussian noise. Why? Because they don't really think about, they don't really understand that there is a place where you can model the measurement noise, right? So now you know, and we'll see how we can fix it later on. For today, we're going to assume that when we do the catalysis problem, we're going to assume that the noise is Gaussian. Okay, but just keep in mind that nobody forces you to pick the noise to be Gaussian. You should just think about it. Okay, what do I measure? How do I measure it? What do I know about the measurement? All right. Interpretation of the posterior. So once you have the prior, once you have the likelihood, the solution of the inverse problem is this: likelihood times posterior divided by that normalization constant. That's it, right? So what is that? How do you interpret it? It is your state of knowledge about the unknown parameters, assuming that your model is correct, of course, right? After you have seen the data. This is how you interpret it. So you started with this state of knowledge, P of X, and through the likelihood, you updated it. Okay? Let's look at the normalization constant. Why do I have it there? So that's Z of phi. This has many different names. One of the names you can use for it is normalization constant, right? Z. Another name that you can use for it is partition function. This is how it's called in statistical mechanics. Another name that you can use for it is the evidence. The evidence name is a little bit strange. It will make sense in 3 or 4 lectures when we see how this Z of phi can be used to do model selection. Later, we will see that this Z of phi is basically proportional to the probability that that model is the right model. So if you have the Z of phi 1 and the Z of phi 2 and the Z of phi 3, by comparing these Z's, you can tell which model is better. So you will see, it will all make sense. It's extremely simple to understand it. I just don't want to talk about it right now. Okay? But it is very natural. It's as natural as likelihood times prior gives you the posterior. It is as natural as that, but let's do it later. Okay? And the reason I'm going to do it later is that even though it is extremely easy to understand what it means when I will show it to you, it is very difficult to compute it. Okay? So it solves everything. It allows you to do model selection, but then you can't compute it. So I'm going to have to give a lecture on how to compute it. Okay? That's why I'll talk about it later. Okay, so why Bayesian? So first of all, the solution always exists. That's it. Okay? So your inverse problem always has a solution. But the solution now is not a point estimate for the parameters, it is a distribution. But it is one thing. It is one thing that has to do with an infinite number of things, but it's one thing, okay? It's a probability density on the space of parameters, all right? The solution is unique. It's one probability density. It may be a probability density that has two modes, right? So the solution in the, which is a probability density, right? It could be like this. But because it is a probability density, it could also be like this. But it's still one thing. But now that one thing is a function, okay? There is a place to enforce or encode, if you like, prior beliefs. It is right there. This was not something that we had in the classical formulation of inverse problems. And there's a huge amount of literature on how to basically force your prior beliefs in classical inverse problems. But here, in the Bayesian approach, it just goes there. You have a likelihood that has a very nice interpretation, right? It models the measurement process. I think this is the fourth time I say that. It is a take-home message, okay? Or the model discrepancy. This is also something that we didn't really have in the classical approach. Quantifies epistemic uncertainties, obviously, because the solution itself is the probability density that corresponds to your state of knowledge about the parameters after you've seen the data. So the uncertainty is already taken care of. All right? It allows model selection. And we will see later on that the key to doing model selection are the normalization constants of two different models. So if you have model F1 and model F2, you calibrate F1, you calibrate F2 to the best of your abilities, you find the normalization constant of corresponding to F1, the normalization constant corresponding to F2, and then by comparing these two, I'll give you the answer. Whichever is bigger is the better one, all right? It's very straightforward. You can select the best model, okay? But of course, how to compute that, it's a big problem, maybe 24, maybe later, definitely before the end of the class, okay? We're gonna see that. Okay, there is only one problem. This thing is not analytically tractable. The only way you can make it analytically tractable, there are two ways. Which is basically one, but we just mention it as if it was two. If this is Gaussian, this is linear, and this is Gaussian, then there is an analytical solution, and it is a Gaussian. Okay? So if your prior is Gaussian, if your model is linear in X, and if your measurement noise is Gaussian, then the posterior is a Gaussian. Sometimes this happens. Most of the times it doesn't happen. There are other cases. If you have so-called conjugate priors, right? This is what you saw in second homework set, right? But this never happens when f of x is a physical model. You never have conjugate priors, all right? Because most of the times it's a black box, or it requires you to solve a partial differential equation. It's very unlikely that you have conjugate priors. Anyway, so there's really two things you can do. Three things that you can do. You can try to approximate this somehow, right? And this is what we're going to do today. We're going to say, let's take this posterior, which it's not necessarily a Gaussian, and let's approximate it with a Gaussian. Thing number one, right? The other thing that we can do is we can say, forget about approximating it. Let's just take samples from it, okay? Just sample from it. It's possible to sample from it. This will give rise to the Markov chain Monte Carlo techniques. Markov chain Monte Carlo techniques, we're going to start looking at the second lecture of this week, tells us how to sample from a posterior. Okay? And if you really think about it, the problem for sampling is this normalization constant, which you don't really know what it is. So you need to sample from a probability density that you know up to a normalization constant. You can evaluate this, but you cannot evaluate that. So can you sample from this by just evaluating the likelihood times prior, right? Yes, it is possible. We'll see it next time. And there's one more way to do it. It's called variational inference. It's the most advanced technique there is in machine learning right now. And of course can be used to calibrate models like physical models or any model whatsoever. And it's may surprise you that it is actually a very old technique. It was invented, almost everything that I'm talking about today, by physicists. It just gave it different names. All right. All right. Yeah, seriously, everything that I'm talking about has been invented in physics, like 100 years ago. Bayesian inference probability theory was invented, at least in the form that we interpret it right now, by Laplace, like 200 years ago, to calibrate his astronomical models. So the first use of probability theory in the modern sense was to calibrate a model. What else? The Laplace approximation obviously tells you something about who invented the approximation, right? And this z here, I write it as z because it's the partition function in statistical mechanics, right? Metropolis algorithm was invented to do statistical mechanics in Los Alamos. What else? The variational inference that we're going to talk about was invented by physicists, again, to do statistical mechanics, and it was called the mean field approximation, etc., etc. All right, so the Laplace approximation. Let me remind you what the Laplace approximation is. So the Laplace approximation takes an arbitrary probability density, and it gives you a Gaussian approximation to it. Okay, how does it work? You take the probability density, you take its logarithm, and you do the Taylor expansions of its logarithm about the maximum of the probability density, and then you truncate in the second term. That's how you do it. So if you don't remember the details, you can go back and look at that lecture. But seriously, all you need to do is take your posterior and maximize it. To maximize it, you don't need to know the normalization constant because it is just a constant, right? So you maximize it, you find the x at which the posterior is maximum, and then you need the second derivative of the logarithm of the posterior, and that's going to give you the covariance matrix. Okay, all these are described earlier on. So, but pictorially, this is what it does. If this was the posterior, it locates this point. At that point, it goes then and it approximates with a Gaussian. It will kind of look like this. Okay, so it's not gonna be perfect, but at least it's gonna be located at the right spot. It's gonna have an okay variance, right? But if your distribution is very skewed, it's not gonna work. If you have more than one modes in your distribution, it's not gonna work, etc., etc. Okay?
So why are we doing this like normal distribution?
Because it's the simplest. So I'm saying, here's what I'm saying. I need to characterize this. What is the simplest? What is the starting point? Well, the starting point is to say that this is approximately a Gaussian. Okay, let me just find a mu and a sigma so that it just, that makes this, that approximates this best. This is what the Laplace approximation does. Okay? And it's really just because I don't want to talk about Metropolis in the same lecture where I introduce the basic concepts. That's the only reason. Okay, but it's still it's the easiest thing you can do. Anyway, so let's just look at some details. If the likelihood is Gaussian, and you assume that you know your sigma, so I'm assuming the variance of the likelihood, I'm assuming that I know it so that I don't have to estimate it, okay? Then this is going to be my likelihood, fine. Then the log of the posterior would look like that, right? So typically the first thing of the Laplace approximation, what is it? It is to maximize the posterior, right? Which is the same as maximizing the log of the posterior. Well, look at what happens if you have a Gaussian likelihood. This is the log of the posterior. When you try to maximize it, you're basically minimizing the square loss. Okay, so it is very close to the classical approach with two differences. There is this sigma square that divides the square loss, and there is a biasing term. And the classical approaches that work add such a biasing term, like Tikhonov regularization, for example, add this biasing term in an ad hoc manner. Okay, so first they added it in an ad hoc manner, and then people thought, well, maybe we can reformulate it in a Bayesian way, and then that ad hoc thing that you add there is basically your prior knowledge. Okay? So this is the Laplace approximation for a Gaussian likelihood, right? So you just maximize the log, that's going to give you your mu, and then your sigma is going to be it's going to come from the Hessian of the log of your posterior evaluated at that mu, and you need to invert that and put a minus sign in front of it. Okay? Because mu is the maximum, this Hessian matrix here is going to be negative definite. You put a minus sign in front of it, it becomes a positive definite matrix, a good covariance matrix. This is it, right? So you need to basically solve this problem with your favorite optimization method, gradient ascent, conjugate gradients, BFGS, Newton-Raphson, whatever you can use, just like the classical approach. The only difference with the classical approach is this biasing term, which was not in the classical approach. And then you need the second derivative, which you can do either numerically or with the method of adjoints. All right. I don't think we really need all of these details, but the second derivative, it's this. You can work it out. I have worked it out because I actually implemented it for the catalyst problem. Anyway, you see that what you really need to get the second derivative, if you follow the chain rule. If you feel uncomfortable with the chain rule, please spend an afternoon on the chain rule. It will pay off, trust me. It is useful everywhere. Okay? This is what you need. So you need the ability to get the second derivatives of your model with respect to the parameters. This may not be trivial, obviously, right? So if you have a PDE or a dynamical system, this is doable with the method of adjoints that we saw last time. You just take one more derivative. You can do finite differences, right, to get the second derivative. But also, the other thing you can do is you can fit your model around mu, fit in the sense you can replace your model with a polynomial chaos approximation, and then differentiate the polynomial chaos approximation. See what I mean? So this is how everything is connected. Whenever something is very hard to do with your model, you can go and say, let me do polynomial chaos, replace my model with polynomial chaos. Well, polynomial chaos is just polynomials. Of course, I can take the second derivative of polynomial, right? And you can do that. All right, so now let's get to the catalyst problem and look at the example. So I'm gonna pick, I need to pick a prior. So remember that these x's here they're not really the reaction coefficients for the catalyst problem. The reaction coefficients are k, right? So these x's are basically defined like that. Now, if I'm not mistaken. So the x's are basically the logarithm of the k times 180 minutes. Okay, k is given in inverse minutes times 180 minutes, which is the total measurement times. Gives me a unitless thing here, of which I'm taking the logarithm. And the reason I'm working with with these variables instead of the k's is because these variables are restricted and the k's are restricted. Whenever you want to optimize something, it's probably best to work with unrestricted variables. Even though, from a Bayesian perspective, there's absolutely no problem. You can just put a density on k that is on the positive k's, okay, with positive support. So we have, one xi for each one of the k's, and we have 6 or 5, I don't remember, reaction coefficients, okay? And then I go to this space and I put a Gaussian distribution there, but so you're gonna tell me, well, why did you pick a Gaussian? And my answer is gonna be because I don't really know what else to pick. This is my answer. And to compensate for the fact that I don't really know what else to pick, I'm gonna set gamma equal to 100. Right? So this really just looks like a completely flat thing in the log space of k's. Alright? And this is totally okay. Because the result is not gonna be very sensitive to what I pick as soon as it is flat. Alright, and of course that sigma there, I didn't really include it in the calibration. I could have included it, but I wanted to keep it out so that I can show you how to include it later. Alright, so for now I just kept it out. I didn't include it as one of my parameters, which I could have done, but I didn't. Okay, just to show you the effect of that sigma. Actually, I picked gamma equal to 10. I'm sorry about that. Even though maybe the figure is wrong and what I wrote before is right. But it shouldn't make a big difference because a variance of 10 is also very big. So this is the fit I get for sigma equals 5, and it doesn't really look good, and that's probably because the assumption that sigma is 5 is not right. Sigma is the standard deviation of the noise. You see here that the scale is 500 in terms of concentration, so 5 is probably too small, right? So what is the level of the noise? Well, if you look at, shouldn't it be something like 10% of 500, which is definitely more than 5, something like, I don't know, 10 at least, or 15 or 20? Yes. Gamma is the prior, okay? So what we're gonna do today is we're going to fix this, and we're also going to fix the measurement noise. Actually, the measurement noise, I'm going to relax it later on. But in reality, there's nothing stopping you for saying, I also don't know what gamma is. So let me put a prior on gamma, make it a parameter for which I'm calibrating. And then you get what is known as hierarchical base models. And we're gonna do that later, right? But for now, we'll just fix it. All right. This is what you get for sigma equals 50. Right, so under the assumption here that the noise is 50, of course, it makes sense. The more noise you have, the more difficult it is to pinpoint exactly what your model is, right? So here you see, what you see here are responses, model predictions with parameters being sampled from the approximate posterior, from the Laplace posterior. So I compute the Laplace posterior, I sample 50 times, I show you 50 samples, just to see how well it matches the data. Well, the right parameter for sigma is around 20, 15, 12, it's in the range of 10 to 20. So for 20, this is the fit we get. Okay, but we're not now much better than, following the classical approach, because we haven't discussed about the selection of sigma. Anyway, so let's just select sigma. So to select sigma, we do not panic. We say sigma is just another parameter. So if instead of just having x, I just have x and something else. Alright? So you can do exactly the same thing with x and something else. And of course, the first thing you need to do is put a prior on sigma. Here I'm putting this prior on sigma, which is not, strictly speaking, a distribution. It is not a density because it doesn't integrate to 1, it integrates to infinity. It is called an improper density, but it's the so-called Jeffreys prior. It has a special density that should be used for parameters that are scales, like sigma is a scale parameter, right? It should be used for parameters that are scales when you have no other information about them. Okay, we introduced that, I think, in the first 2 or 3 lectures. Anyway, so 1 over sigma, proportion 1 over sigma for sigma. Now, what we're going to do is we're going to make sigma one more parameter. We're going to follow the Laplace approximation, which requires us to maximize something, maximize the posterior. And we don't like maximizing with constraints. So instead of working with sigma, we're going to work with log of sigma. Okay? So we're going to introduce here a parameter that is just the log of sigma. So it's just like I did with K's, right? So instead of working with the reaction rates, I said, let me work with the logarithms of the reaction rate so I don't have to worry about the fact that they are positive. I do the same thing with sigma. Sigma is positive, it's positive, I don't want to have to worry about it. Let me just work with the logarithms of sigma. Okay? And this is the kind of thinking that you must be doing before you even start solving your problem. Right? Don't just program your problem, say this is the thing that I want to maximize. Let me try to do that. You do it, you spend, I don't know, like a week to try to do it, and then, of course, it doesn't work. And then you start, changing things until you make it work, and then it kind of works. And then you try to use a different data set, and it doesn't work. This is what happens when you do it like that. All right? But if you think about it and you say, okay, before I even program it, how can I make my life easier? Why do I have to add constraints to my optimization when I can just work with the logarithms? Right? That's how you think. Anyway, so if this is the probability density you put on sigma, then you can ask yourself the question, what is the probability density that I should put on theta? And this is something you can just answer with probability theory. It's a formula. You can find it in Wikipedia. It's called the change of variables formula for probability densities. If you know the probability density of sigma, and then you take theta, which is log of sigma, what is the probability density of theta? This is the formula. Okay? And it turns out that the probability density for theta is 1. It's proportional to 1. And this is why Jeffreys prior is a non-informative prior, right? So you see that you applied a transformation to it that took you from the positive variables to the real line, and it basically gave you an uninformative density on the real line. And this is how it was constructed, so it gives you uninformative priors when you transform with monotonic transforms. Anyway, cross that out. Okay, so now what we're going to do, what do we have? Well, I'm going to introduce z, which is just x and theta together, okay? And now I will think of that z just like I thought about my x before. Now I just have to talk about the posterior of z. So that is the posterior of z, right? The posterior of z proportional to the likelihood of my data given z times the prior of z, and it turns out to be like that. Right? There's no prior of theta because prior of theta is proportional to 1. So it disappeared. And then you do the Laplace approximation on that. Right? So Laplace approximation requires you to maximize this function over z. Okay? So that is over x and theta. And you do that. And if you do that for a specific gamma, you're going to find this sigma. Okay? And of course, with a little bit of error for that sigma. So now you estimated the measurement noise as well, with uncertainty. Right? So this technique helped us estimate the reaction coefficients with uncertainty and the noise with uncertainty. Okay? And if you look, I want you to appreciate the symmetry that the noise parameter was treated in exactly the same way as all the other parameters of your model. It's a legitimate model parameter. Okay, so your model is not just the physics, it's the physics and the measurement process. So you have your parameters for the physics, you have your parameters for the measurement process. It's fine if you want to distinguish between the two, because you probably care about the physical parameters than the noise parameters. You probably care more about that. But from an inference perspective, from a Bayesian perspective, these two parameters are the same, are just parameters, right? And you can have a third set of parameters if you wanted to. Like the parameter of the experimentalist trying to trick me, for example. Whatever, right? It's totally fine. You could also add that. Or the parameters of my student cooking up the data. You could add that as well. Nobody does that, I know. At least now you know that how not to cook your data. All right. There are some issues with the Laplace approximation that remain. And of course, let me just be blunt about it. There are absolutely no issues with the Bayesian approach to inverse problems. Absolutely no issues. It is the right way to solve inverse problems, period. Okay? Of course, it's not easy to apply. That is its problem. Okay? That it is not easy to apply. The Laplace approximation is an approximation to the fully Bayesian solution of inverse problems. Therefore, it has problems. And whatever is an approximation to the Bayesian inverse problems will have problems. See what I mean? The Bayesian formulation of inverse problems is the right thing to do. It is like a dogma, okay, if you like. It is just right, okay? You just have to accept it. But as soon as you approximate it, your approximation is going to be wrong. It's just how things are. You want to use the Laplace approximation, your approximation is going to have problems. So there's going to be a specific regime where it's going to work. The Bayesian approach, if you could do it fully, it will work everywhere. Because you cannot do it fully, you're going to have some problems with the Laplace approximation. Same thing when you sample, right? So when you sample, you're approximating the posterior with samples. This is going to have its own problems. All right? So I said the Bayesian formulation is correct. That is absolutely true. This is how it should be. But of course, it depends on your input. And your input may be wrong. Right? So even though the formulation of the problem is absolutely correct, you may make mistakes in the formulation of the prior. And what is the mistake you can make in the formulation of the prior? You may assume things that you do not really know. Right? So if you are more certain than you should really be, then you're going to get garbage, right? So if, for example, you tell me, well, I know that x cannot really be greater than 10, therefore I'm going to put zero prior probability that x is greater than 10, but then in reality x is 12, you're going to get garbage, right? And this is totally okay. It's not a problem of the Bayesian formulation. It's a problem that you do not really, you think you knew something that you didn't really know. That's the problem, right? You thought that you knew that x is greater than 10, but basically all that happened is that you believed falsely and you were extremely certain about it that x wasn't greater than 10. But you were just wrong. Okay? This is what happened there. And the other thing that can mess things up a little bit is when you formulate your likelihood. Well, the Bayesian approach will work, but if you assume a model for the measurement process that it's not the right model, of course it's not going to work, right? So if you tell me that the measurement process is giving me a Gaussian noise with a variance of 10 to the minus 6 when the real variance is 100, you're going to get garbage, right? And the same thing about your physical model. Your physical model may be wrong, right? If your physical model is wrong and you do not account for the possibility that it is wrong, you're gonna get garbage. Make sense? So if you're suspecting that your physical model is wrong, it's your responsibility to say how it could be wrong. So you can say, for example, f of x may not really be what is going on. There is some physics that I don't understand. So what I measure is really f of x plus g of x, where that g is something that I don't really understand at the moment. But I know that it is there because I know that my understanding of the physics is incorrect. So then that the g of x, you have to model it, but of course because you don't understand the physics, you probably have to pick a statistical model for that g of x, that correction term, right? And you will go on like that.
So how is this method helping us to find the number of intermediates?
The number of what?
Selecting the number of intermediates, x, y. Like initially you were saying in classical model, we can't tell how many intermediates.
I am not talking about experimental design right now, right? So how you select your x and your y.
No, I'm speaking about like selection of f of x. Like
yes.
How many intermediates reactions?
So f of x here is not this f of x. I mean, I understand that this may be confusing, but this f of x here is your model, right? X are parameters that are actually frozen in time, frozen parameters that you don't know. And f of x is just that, right? So, and the form of f of x is known to you. We just do physics, and you know what it is. Okay, anyway, just understand that it's probably better not to talk too much when I don't have something to show, because then I'm probably the only person that understands what I'm talking about. So, forget about the details that seemed a little bit... Alright, so with the Laplace approximation in particular, what are the problems, right? So it underestimates uncertainty. It's because you have a posterior that has all the nice uncertainty, and then you fit it with a Gaussian, and then you're gonna miss a little bit of the tails of that posterior. It does not work when you have strong correlations between the components of x. You'll see what I mean by that. So in some physical models, for example, you because the x's, the parameters are physical quantities themselves, they must satisfy certain relations. So you cannot have, most of the times, when you are dealing with physical models and you have an x1 and an x2, sometimes only a set of parameters make sense and not all of them, right? So just because of the physics, sometimes there is a manifold of the space of parameters where that x should be, and anything else doesn't really make sense because the physical model would not work. Okay? And this you may or you may not know it, but the Bayesian the Bayesian formulation will take care of that. The Laplace approximation will not. It does not work when the posterior is multimodal. Of course, when you have, two peaks in your posterior, this will pick just one of them. And it is a crude approximation to the true solution of the inverse problem, and this is what I talked about. I spent like 10 minutes talking about that without showing you anything, okay? That's pretty much it. Now what comes next, and this is really, really, really exciting, right? And that's what we need to learn. And this is where we're gonna go ridiculously slowly, starting next time. Markov chain Monte Carlo, which allows us to sample from the posterior. And with Markov chain Monte Carlo, you're going to be able to calibrate any model you want the right way without being afraid of the computation, of the complexity, okay? There's still the computational complexity of your physical model. If it takes a day to evaluate it at a single point, well, you're going to have to replace it with something cheaper. But it's extremely powerful. The only problem is that, again, if you are completely agnostic about what goes on inside Markov chain Monte Carlo samples, you're gonna get garbage. Okay, because Markov chain Monte Carlo is based on a famous paper by Metropolis 1953 that guarantees that his algorithm is going to always give you samples from the posterior, but only if you take an infinite number of steps. Okay? So, and this is how it works with, it goes with powerful mathematical statements. They only work in the limit of infinite samples. And because we're going to have to stop that algorithm at some point, you kind of have to tune it. And it is possible to tune it, but you need to understand what happens. There are 3 or 4 choices that you have to make. And I'll guide you. I mean, I will not focus so much on the theory, but I'll try to guide you on picking these parameters in practice. And we're going to spend definitely at least 2 lectures. We're going to spend at least 2 lectures on Markov chain Monte Carlo, maybe 3. Because I want to spend the first 2 lectures on showing you the basics, where we're actually going to program the solvers, the sampler ourselves, just to see how simple it is. And then I want to spend 1 lecture showing you a package called PyMC that allows you to set up a probabilistic model and calibrate it almost automatically, almost with like 5 minutes. Okay, so we'll do that as well. I don't know, maybe, are you familiar with PyMC? Maybe I shouldn't put you on the spot. We'll talk about it later. But I definitely want to show you PyMC. So maybe we'll do 3 lectures on Markov chain Monte Carlo. And this is what you're going to use in your homework. And then the only problem with Markov chain Monte Carlo is that it doesn't estimate that z of f, the partition function, the normalization constant. It gives a lousy estimate of that z of f. It gives you an estimate with an infinite variance. Do you remember what we did in Monte Carlo, where there was a problem where we had an estimator with an infinite variance? It gives you an estimate like that, so you can't really trust it. And for that, we're going to have to introduce sequential Monte Carlo methodologies, about which I'll talk to you later. And after we do that, then we'll introduce variational inference. All right? Now, for example, I don't know about, and then we have like two more lectures, where we're going to talk about optimization. Just something that I want to say right now. Apart from, I know that Alana works on model estimation but her model is a dynamical system that she partially observes over time, right? So one of the approaches to solve this problem, which is a calibration problem essentially, is Kalman filters. So is there anybody else working on Kalman filters or have heard about that at all? Okay. So just for those who work on Kalman filter type of problems, where you basically have time measurements that are not directly do not directly come from your system, but they are a perturbation, noisy function of your system, right? This formulation still works. This is still the right thing to do. Okay? It's still the right formulation of this problem is to pose to use the Bayesian formulation and write down the posterior of your parameters of any hidden stage of your model. This is the right thing to do. But none of these techniques will work because of the dimensionality of the random variables that you have. Right? So these would work when you have, I don't know, 10, 50, 100 parameters, but in filtering problems, you have thousands of parameters. So these do not work. The sequential Monte Carlo approach can be modified to work in these cases. But in general, in cases where you have a lot of parameters, then you need to do a little bit of more math. We'll see if we can spend a lecture on this. It depends on how we go with all that.